Welcome to Cosmic Sedation, your peaceful retreat into the cosmos. Tonight, we explore the cosmic horizon where cooling white dwarfs find their equilibrium across the stars. Enjoy this soothing journey through space. Don't forget to subscribe and like if you're enjoying the ride. It helps us keep dreaming big. Where are you listening from tonight? And what time do you usually drift off? Let's begin our calm and unhurried cosmic adventure together. Amidst the scorching heat of a collapsing white dwarf, a cooling process unfolds, gradually dimming its once vibrant glow across the cosmos. This paradoxical dance between collapse and cooling is a testament to the intricate balance maintained by electron degeneracy pressure, which prevents further compression beyond the star's current size. Consider this. At their core, these cooling stars are as hot as 30,000 degrees Celsius, yet they continue to lose heat. Over billions of years, white dwarfs slowly cool down to below 3,000 Kelvin, a process that mirrors the gradual fade of a candle's flame after it is extinguished. For a human observer, this would be an almost imperceptible change, akin to watching ice melt at minus 230 degrees Celsius, so slow and so cold. The oldest known white dwarf is around 10.5 billion years old, older than our solar system by nearly 4 billion years. A typical white dwarf has a radius similar to Earth's, but contains mass comparable to the Sun. This extreme density means that a teaspoon of white dwarf material would weigh approximately 5 million kilograms on Earth. The iron in your blood was once part of this starry process, forged in the heart of an ancient giant before its death and rebirth as a white dwarf. Some white dwarfs can take up to 8 billion years to cool down completely after their formation. Imagine a sphere with a radius of 8,000 kilometers housing more mass than our entire solar system minus Jupiter. This remarkable density is due to the crystalline structure of carbon and oxygen within these stars, akin to diamonds in their purest form. As they cool, these white dwarfs slowly contract, an effect that could take trillions of years for a human to perceive, yet it reshapes them over cosmic time scales. The cooling process has no end within our observable universe. Intriguingly, some white dwarfs emit X-rays if they accrete matter from a binary companion. This seemingly paradoxical phenomenon occurs despite their cool temperatures of 30,000 Kelvin or less. Their interaction with nearby stars adds complexity to these cooling bodies, creating a dynamic interplay between radiation and accretion that continues long after the star's nuclear fuel has been exhausted. While sound cannot propagate in the vacuum surrounding white dwarfs, their cooling process is marked by an ongoing transformation. The heat transfer across space occurs solely through radiation, with no molecules to carry pressure waves. This method of energy transport ensures that these ancient stars continue to shed their remaining warmth into the vastness of space, a silent yet persistent reminder of their once luminous past. Additionally, when white dwarfs reach temperatures below 3,000 Kelvin after approximately 10 billion years, they emit less radiation and fade further from view, becoming some of the coldest objects in the universe. Notably, this cooling process can lead to the formation of crystalline structures within the star's core, similar to diamond-like carbon and oxygen arrangements. The cooling process within these stars not only affects their luminosity, but also influences the fate of nearby celestial bodies. For instance, if a white dwarf were to accrete too much mass from its companion star, it could potentially exceed the Chandrasekhar limit, precisely 1.4 solar masses, and collapse into a neutron star or even a black hole. However, as long as electron degeneracy pressure maintains equilibrium, the white dwarf will continue to cool and contract for trillions of years, offering us a glimpse into the life cycle of stars and their eventual transformation into cosmic embers. Imagine an object the size of Earth, yet it contains as much mass as our entire Sun. This extreme density is found in a white dwarf, a remnant of stars that have exhausted their nuclear fuel. As these stellar corpses cool over billions of years, they reach temperatures so low that sound cannot propagate through them due to the vacuum of space. The cooling process itself slows down drastically, with some taking up to 8 billion years to fully cool. In this environment, heat transfer occurs only via radiation, a reminder of how different thermal dynamics can be in space compared to Earth. The density of these white dwarfs is extraordinary, even by cosmic standards. A teaspoonful of white dwarf material would weigh about 5 million kilograms on Earth, equivalent to the mass of nearly 50 blue whales. This compression rivals that found within atomic nuclei, where protons and neutrons are packed tightly together. The crystalline structure of carbon and oxygen in white dwarfs means they resemble giant diamonds floating in space. In this sense, these stars have transformed into cosmic jewels, their dense cores frozen in time. Beyond mere size and mass comparisons, the cooling process within a white dwarf is a complex interplay between temperature and pressure. Electron degeneracy pressure halts further gravitational collapse, maintaining the star's current state of equilibrium. This balance prevents any additional compression despite the relentless cooling. The surface temperature of these white dwarfs can drop as low as 230 degrees Celsius below zero, cold enough for xenon to become a solid at Earth's standard atmospheric pressure. In this environment, the material is so tightly packed that it defies our usual understanding of matter and density. As we delve deeper into the structure of a cooling white dwarf, consider what happens on its surface. Despite their high temperatures compared to Earth's coldest regions, the vacuum of space means there would be no air or water for heat conduction or evaporation. A human body exposed to such conditions would suffer from hypothermia and loss of consciousness within minutes. Yet, the internal structure of these stars is far more fascinating, crystalline in nature, with a lattice arrangement similar to that found in diamonds here on Earth. This crystallization process is not just an aesthetic curiosity. It's crucial for maintaining the star's stability as it cools over time. The oldest known white dwarf is approximately 10.5 billion years old, older even than our solar system, which formed around 6 billion years ago. These ancient stars have existed for nearly half the age of the universe itself, bearing witness to epochs long before Earth was conceived. They are relics from a time when the cosmos was younger, hotter, and more active with star formation. The cooling process of these white dwarfs is not only a journey through deep time, but also one that connects us directly to the origins of the elements within our bodies. Iron in your blood, carbon in your cells. These were forged in stars much larger than our sun, which have since expired and left behind such dense remnants. The cooling of a white dwarf is not merely a passive event. It's part of an intricate cosmic timeline that stretches from star birth to eventual death. After billions of years, these stellar corpses will continue to cool until they reach a point where their radiative emissions become negligible. At this stage, the white dwarf would be considered a black dwarf, an object so cold that it no longer emits any appreciable radiation. However, given the current age of our universe, not even a single black dwarf has been observed yet, as all known cooling white dwarfs are still emitting detectable light. In their final stages, these stars serve as time capsules from the early universe, offering clues about the formation and evolution of galaxies across cosmic history. In the quiet vastness of space, an astronaut floats near a cooling white dwarf, feeling its faint gravitational pull like a subtle pressure on their suit. The force exerted by this remnant star is minuscule, akin to standing on a gently sloping hill rather than the solid ground beneath our feet. Yet, it comes from an object with a radius similar to Earth's, but containing as much mass as the Sun, over 100 times denser than iron. This extraordinary density creates a gravitational field that subtly influences every atom in their body. As they drift through the vacuum, time itself is stretched by the white dwarf's gravity. Light bends ever so slightly around this celestial object, an effect known as gravitational lensing. While imperceptible to human senses, this phenomenon illustrates how mass warps spacetime, a revelation first described by Einstein. The cooling star's faint glow falls just beyond visible light, emitting infrared radiation that is invisible to the naked eye. The astronaut experiences this pull as a subtle reminder of the immense scale and age of cosmic processes. This white dwarf formed billions of years ago from the collapse of a larger star, its core now stabilized by electron degeneracy pressure. The cooling phase will last for trillions more years, during which it will gradually dim until it becomes an inert black cinder. Each breath taken in this environment is a quiet acknowledgement of the balance between gravity and motion. In contrast to the bustling activity within their body, the white dwarf's crystalline core, a lattice of carbon and oxygen atoms locked in perfect order, represents a state of near-perfect stability. This structure, similar to diamond, but on an astronomical scale, holds its form against the relentless passage of time. The astronaut's journey through this quiet expanse is marked by a profound sense of solitude. They are surrounded by a universe that operates on timescales far beyond human comprehension. Events like galaxy formation and black hole mergers occur over billions to trillions of years. For instance, the merging of two supermassive black holes can take up to 10 billion years. As they continue their journey away from the white dwarf, the astronaut might notice slight variations in the pull due to tidal forces. These minute changes are akin to feeling the difference between standing at the equator versus near the poles on Earth. The differential force stretches and compresses the suit ever so slightly. a demonstration of how gravity can vary across different points in space. The cooling white dwarf is not only a beacon of ancient stellar processes, but also a site for potential discovery. Scientists hypothesize that certain white dwarfs might host planetary systems or could have once had them, adding another layer of complexity to the story of star formation and evolution. The astronaut's presence near this celestial object serves as a bridge between human curiosity and cosmic exploration. The cooling white dwarf is composed primarily of carbon and oxygen arranged in crystalline structures, much like diamonds on Earth. This rigid lattice structure forms due to electron degeneracy pressure, which resists further compression once the star has shed its outer layers. The surface temperature of this particular white dwarf has dropped below 3000 Kelvin, making it emit light in wavelengths invisible to human eyes. Despite being a mere speck compared to the vastness of space, the gravitational influence of the white dwarf is profound. It gently tugs at every molecule within the astronaut's suit, an effect that would be imperceptible on Earth, but becomes noticeable in this environment. The pull creates a sense of connection between the distant star and the human presence near it. As they continue their journey away from the white dwarf, the gravitational influence diminishes gradually, eventually becoming undetectable. This fading force serves as a reminder of the delicate balance maintained by electron degeneracy pressure, which keeps the star's core stable against further collapse. The process is both ongoing and eternal for trillions more years until thermal equilibrium is reached. The cooling white dwarf represents one of many such celestial objects that dot our universe, each with its own unique history and future. These remnants are not just passive observers, but active participants in cosmic evolution, contributing to the formation of new stars and planetary systems through their eventual dispersal of elements. The astronaut's proximity to this cooling star is a fleeting moment in an unending cycle. The white dwarf's surface temperature continues to decrease at a rate determined by its mass and composition, with less massive objects taking longer to cool down completely. For instance, a white dwarf with half the Sun's mass would take approximately 10–14 years to reach thermal equilibrium, while one with twice the Sun's mass could do so in around 10 billion years. In the heart of a cooling white dwarf, electrons are caught in an extraordinary quantum dance. They press against each other with such force that classical physics fails to explain their stability. Instead, it is the principle of electron degeneracy pressure that holds these stars together, defying gravitational collapse. This pressure operates at scales far beyond human comprehension, akin to compressing all the air from a room into a space no larger than a grain of sand. Remarkably, this principle also underpins the structure of neutron stars, though at even more extreme densities. The oldest known white dwarf, around 13.8 billion years old, predates our solar system by nearly 4 billion years. At the core of these stellar remnants, temperatures hover around 13.8 billion degrees Kelvin during their formation, but plummet to just over 2000 Kelvin as they age and cool. This cooling process is slow yet relentless, taking upwards of 10 billion years for a typical white dwarf to reach this cooler state. The iron in our blood shares an origin with the carbon and oxygen that make up these stars. Both were forged in the cores of other ancient stars before being scattered across the universe. These elements are now part of planets, including Earth, linking us directly to the cosmic processes that shaped our world. The surface of a cooling white dwarf is a peculiar landscape, devoid of any material atmosphere, but instead covered by a crystalline lattice of elements. This solid-state structure resembles diamonds found on Earth, yet spans planetary scales. The pressure at these depths exceeds 10 million atmospheres, creating conditions where matter behaves in ways defying common understanding. Each crystal represents a frozen moment in time, holding the memory of the star's fiery past. These crystalline structures are not just remnants, but also cosmic archives, preserving the history of stellar evolution. White dwarfs exist in a delicate balance between gravitational compression and quantum resistance. Once they reach this equilibrium, any further collapse is halted by the Pauli exclusion principle, which dictates that no two electrons can occupy the same quantum state with identical properties. This balance ensures these stars will not suddenly implode into neutron stars or explode as supernovae unless accreting additional mass from a companion star. The stability of electron degeneracy pressure also means white dwarfs can outlast our Sun by many billions of years, cooling slowly to become dark stellar remnants. They serve as cosmic timekeepers, their cooling rates providing astronomers with a tool to measure vast stretches of time and space. However, despite this stability, some white dwarfs exhibit unexpected magnetic fields that are thousands of times stronger than Earth's, challenging our understanding of how such intense magnetism can arise in these compact objects. Despite their extreme conditions, these compact objects influence the universe in subtle ways. In carefully calibrated laboratories on Earth, scientists can recreate similar conditions under controlled environments. This allows researchers to study the behavior of matter at these quantum extremes without venturing into distant galaxies. Each teaspoonful of white dwarf material would weigh about 5.6 million kilograms on Earth due to its immense density, a stark reminder of the incredible forces at play within these stellar remnants. The pressure inside is so intense that it could crush mountains into dust. However, this same principle keeps stars from collapsing further by maintaining an equilibrium where each electron occupies a unique quantum state, preventing any two electrons from sharing the same energy level. In this environment, sound cannot propagate because there are no molecules to carry pressure waves. Heat transfer across space cannot occur through conduction or convection due to the vacuum of space. Radiation is the only method of energy transport. This isolation highlights how profoundly different conditions in a white dwarf are from those on Earth. Yet, these stars remind us of our own cosmic origins, as elements formed within them eventually became part of planets, including our home. The cooling process of white dwarfs provides astronomers with precise tools to measure vast stretches of time and space, offering insights into the universe's age and expansion. In the quiet expanse of space, Cooling white dwarfs serve as cosmic clocks, offering precise age markers for star clusters across galaxies. Their luminosity diminishes steadily over billions of years, allowing astronomers to calculate the age of stellar populations with remarkable accuracy. Each white dwarf cools at a rate that depends on its initial mass and temperature, much like how an old-fashioned clock might slow down or speed up based on its internal mechanisms. The oldest known white dwarf is around 13.8 billion years old, predating our solar system by nearly 4 billion years. This ancient relic provides insight into the early universe's stellar nurseries. Remarkably, these cosmic clocks not only observe passively, but also actively contribute to their environment through thermal radiation. As they cool below 10 million Kelvin, white dwarfs emit infrared light detectable from Earth despite traveling distances of up to 100,000 light-years across galaxies. This radiation is crucial for astronomers who use it like a fingerprint to identify the age of star clusters. Imagine an object with a radius similar to Earth's, roughly 8,000 kilometers, but containing as much mass as our entire Sun. Each cubic centimeter of white dwarf material weighs more than 5 million kilograms on Earth due to its immense density, which is maintained by electron degeneracy pressure, preventing further compression beyond the star's current size. Some cooling white dwarfs emit X-rays if they are part of binary systems, where matter from a companion star falls onto their surface. Despite being cool, reaching temperatures as low as 30,000 Kelvin in some cases, their X-ray emissions allow astronomers to study them even when they would otherwise be too dim to detect. This radiation reveals the intricate dance between the white dwarf and its companion, influencing each other's evolution over time. White dwarfs are composed primarily of carbon and oxygen arranged in a crystalline structure, similar to diamonds found on Earth. As they cool, these crystals slowly settle into an ordered pattern within their cores, creating an internal lattice that is both rigid and stable. This unique formation process means that each white dwarf carries not only the age of its star, but also a record of its stellar nucleosynthesis, providing clues about the elements present in earlier generations of stars within galaxies. The cooling process of these cosmic clocks varies significantly based on their initial mass. For instance, a typical white dwarf cools to below 3,000 Kelvin after approximately 10 billion years, while some take up to 8 billion years to cool completely. This difference highlights the variability in stellar evolution and offers astronomers valuable insights into the life cycle of stars. Moreover, cooling white dwarfs can offer clues about the origins of elements found on Earth. The iron in your blood was forged in a star that died before our Sun existed, and its remnants now exist as part of these cooling relics. This connection between the ancient universe and modern life underscores the profound interconnectedness of cosmic processes and terrestrial existence. As white dwarfs cool, they transition from emitting ultraviolet light to infrared radiation, marking their transformation across the electromagnetic spectrum. This shift in emission allows astronomers to classify them based on their spectral properties, providing a detailed timeline of their cooling history. Each stage of this process is like reading the pages of an ancient book, revealing stories of stars long since extinguished. The ultimate fate of these cosmic clocks lies in their gradual transition from white dwarfs into black dwarfs, hypothetical objects that would no longer emit light once they have cooled to temperatures below 1 Kelvin. While this stage has yet to occur in the observable universe due to its young age, it serves as a reminder of the vast timescales involved in cosmic processes and the enduring nature of these stellar remnants. In conclusion, cooling white dwarfs are more than just ancient stars. They are timekeepers that record the history of star clusters across galaxies. Their precise cooling rates provide astronomers with invaluable tools to measure the age of stellar populations, offering a glimpse into the universe's past and its ongoing evolution. Each white dwarf cools at a rate that depends on its initial mass and temperature, much like how an old-fashioned clock might slow down or speed up based on its internal mechanisms. The oldest known white dwarf is around 13.8 billion years old, predating our solar system by nearly 4 billion years. This ancient relic provides insight into the early universe's stellar nurseries, specifically the conditions under which the first stars formed. Remarkably, these cosmic clocks not only observe passively, but also actively contribute to their environment through thermal radiation. As they cool below 10 million Kelvin, white dwarfs emit infrared light detectable from Earth despite traveling distances of up to 100,000 light-years across galaxies. This radiation is crucial for astronomers who use it like a fingerprint to identify the age of star clusters. Imagine an object with a radius similar to Earth's, roughly 8,000 kilometers, but containing as much mass as our entire Sun. Each cubic centimeter of white dwarf material weighs more than 5 million kilograms on Earth due to its immense density, which is maintained by electron degeneracy pressure, preventing further compression beyond the star's current size. Some cooling white dwarfs emit X-rays if they are part of binary systems, where matter from a companion star falls onto their surface. Despite being cool, reaching temperatures as low as 30,000 Kelvin in some cases, their X-ray emissions allow astronomers to study them even when they would otherwise be too dim to detect. This radiation reveals the intricate dance between the white dwarf and its companion, influencing. In the cold embrace of interstellar space, a white dwarf drifts like a slowly extinguishing candle, its surface temperature dropping from over 13,000 Kelvin to below 3,000 Kelvin over billions of years. Each photon emitted is stretched across distances up to 10 billion light-years by the expansion of space itself, causing their wavelengths to shift into longer, less energetic forms of radiation. Yet this cooling process does not occur uniformly. Some regions cool faster than others, creating subtle patterns on their surfaces that astronomers can detect from Earth. 1 billion years ago, these stars were massive supernovae, their cores collapsing into dense remnants with masses up to 1 4/10 times that of our Sun. Today, they are dim embers, cooling in the darkness of space, a stark reminder of stellar evolution's finite nature. While they once emitted more energy than entire galaxies, now they contribute less light than a single distant star. Remarkably, These remnants contain about as much mass as our Sun, yet are compressed into an object roughly the size of Earth, a density that would crush any matter not held together by degeneracy pressure alone. This compression is so extreme that a teaspoonful of white dwarf material weighs over 5 million kilograms on Earth. The cooling process within these stars is driven solely by radiation, with no conduction or convection to speed it along. The vacuum of space ensures that heat transfer occurs only through the slow emission of photons into the void. This method of energy loss is incredibly inefficient compared to processes we might witness on Earth. In fact, for a white dwarf to cool from 10,000 Kelvin to 3,000 Kelvin takes about 8 billion years, an eternity by human standards, but merely a fraction in cosmic terms. The cooling timeline is not linear. It slows down as the star loses less energy over time, reflecting its gradual approach towards thermal equilibrium. Around us, these cooling remnants are spread across galaxies like ancient candles flickering out one by one. They serve as markers of stellar history, each representing a once massive star that has completed its life cycle. In our own galaxy alone, there are billions of white dwarfs, most older than our solar system. These stars have been cooling for longer periods, their surfaces now so cool they emit mostly infrared radiation rather than visible light. Some may still radiate X-rays if they accrete matter from a companion star, a rare occurrence that briefly warms them once more before the long descent back to darkness. The future holds an even quieter fate for these cooling stars. A billion years from now, many will have cooled below 3,000 Kelvin and become black dwarfs, stellar remnants that no longer emit any detectable radiation. This phase is theoretically possible, but unlikely to be observed directly given the age of our universe. The transition into a black dwarf marks the end of their active role in stellar evolution, as they simply cool further without any significant changes. Each white dwarf's journey from supernova to ember encapsulates the vast timescales and transformations inherent in cosmic processes. While these cooling remnants quietly fade away, they leave behind a legacy of elements essential for life. The carbon and oxygen within them were forged in the cores of massive stars before their explosive deaths. This means that the iron in your blood was created from the ashes of ancient supernovae, long before our sun formed. These white dwarfs are thus not just passive embers, but the carriers of elements vital for life across the universe. In the depths of space, cooling white dwarfs emit thermal radiation even as they grow colder over billions of years. This process is paradoxical. Objects typically cool by emitting heat until they reach equilibrium with their surroundings. But in a vacuum, there are no surroundings to absorb that heat. Instead, these remnants radiate photons into the emptiness of space. Once a white dwarf's surface temperature drops below 3,000 Kelvin, it begins to emit thermal radiation at wavelengths beyond visible light, primarily in the infrared spectrum. This emission continues long after its core nuclear reactions have ceased, marking time like an ancient clock. The cooling process is gradual, with some white dwarfs taking up to 8 billion years to reach this stage, a testament to their enduring presence in the universe. At a distance of 10 light-years, A typical cooling white dwarf appears as faint as a distant pinprick of light to human eyes. Yet, it emits thermal radiation that stretches far beyond this immediate vicinity, potentially reaching other star systems and contributing infinitesimally to the cosmic microwave background. This subtle glow is part of what gives space its slight warmth, even in the depths of interstellar voids. Despite their faintness, these emissions are a reminder of the countless stars whose lives have come to an end. As electrons in a cooling white dwarf settle into a crystalline structure, similar to that found in diamonds, they contribute to the star's overall stability and its unique form of energy release. This crystallization process does not occur within a human timescale, but spans epochs far longer than any civilization could witness. In this state, the white dwarf emits thermal radiation more efficiently than it would if it were still composed of diffuse gas. The crystalline structure also gives the white dwarf an internal rigidity that prevents further collapse once it has reached electron degeneracy pressure equilibrium. Astronomers measure these cooling rates by tracking the dimming light of known white dwarfs over decades and centuries, using this data to refine models of stellar evolution. Each measurement is a small piece of evidence in the grand puzzle of understanding how stars age and die across the cosmos. For instance, one particular white dwarf, known as SDSS J1240 plus 6710, shows signs that it has cooled at an unusually rapid rate for its mass, suggesting some unknown mechanism may influence its cooling process beyond simple physics. This anomaly prompts further investigation into the precise conditions under which stars evolve and eventually cool to darkness. The crystalline nature of white dwarfs also means they are among the densest objects in the universe, with a teaspoonful containing an unimaginable 5.6 million kilograms. Despite their immense density, these stars emit radiation that spreads outward at the speed of light, carrying information about their age and history across the vastness of space. This radiation is not only a scientific tool, but also serves as a quiet reminder of the life cycle of stars, from their birth in stellar nurseries to their eventual cooling into these cosmic embers. In the vastness of space, where stars have long since exhausted their nuclear fuel and cooled into embers, X-ray telescopes detect a faint glow that eludes human vision. This glow emanates from accretion disks surrounding white dwarfs, stellar remnants that once burned brightly in the cosmos. These disks are formed when material from companion stars spirals inward toward the white dwarf, generating intense heat and emitting X-rays. Each X-ray photon detected provides insights not only into the current state of these cooling stars, but also into their dynamic history within binary systems. For example, some white dwarfs exhibit periodic increases in X-ray emission, indicating recent accretion events from companion stars that are still evolving. These bursts can last for years before subsiding as the system stabilizes again. Surprisingly, the coldest known place in the universe is not found here, but on Earth, in laboratories designed to study quantum effects at near absolute zero temperatures. Meanwhile, white dwarfs can emit X-rays despite their cooling surfaces, which have dropped below 3000 Kelvin. This emission results from friction and heating caused by accreted material falling into a compact object with immense gravity. These X-ray emissions offer more than just snapshots of present conditions. They reveal the complex history of interactions within binary systems. For instance, sudden increases in X-ray intensity might signal recent mass transfer events or changes in orbital dynamics between the white dwarf and its companion star. Such bursts can last for years before returning to a quiescent state. Each accretion disk around a white dwarf contains material that was once part of an ancient star's core. This recycled iron, along with other elements, forms new celestial systems, illustrating the universe's recycling process on a cosmic scale. The interconnectedness of all celestial objects is highlighted by these observations, emphasizing how elements formed billions of years ago are repurposed into new stellar systems. Despite their cooling nature, some white dwarfs continue to emit X-rays due to ongoing accretion events. These emissions provide astronomers with invaluable data about stellar evolution and the eventual fate of stars like our Sun. By studying these ancient embers, we gain a deeper understanding of how galaxies evolve over billions of years through the intricate dance of star formation, life, and death. In the quiet expanse of space, white dwarfs drift as slowly cooling remnants of once mighty stars. Their surfaces, now dimming with age, emit thermal radiation that stretches across vast distances, carrying information about their past interactions. This radiation includes X-rays from accretion disks, which are formed when material from a nearby companion star spirals inward toward the white dwarf. The process by which this material is captured and heated to such high temperatures is both intricate and energetic. As matter falls into the gravitational well of the white dwarf, it accelerates at tremendous speeds, heating up due to friction and compression. This intense heat generates X-rays that can be detected from Earth, despite the vast distances separating us. It's worth noting that while these X-ray emissions are faint, they offer a window into the complex dynamics of binary star systems. The material captured by the white dwarf is not just any matter. It often includes elements like iron and carbon, which were once part of the core of an ancient star. This recycling process underscores the interconnectedness of all celestial objects. Each accretion event contributes to the ongoing evolution of these stellar remnants. Over time, as more material is captured, the white dwarf can experience periodic increases in X-ray emission, signaling recent mass transfer events or changes in orbital dynamics with its companion star. These bursts provide valuable data for astronomers studying stellar evolution and the eventual fate of stars like our Sun. By observing these ancient embers, we gain a deeper understanding of how galaxies evolve over billions of years through the intricate dance of star formation, life, and death. In the depths of space, a white dwarf floats in equilibrium, its mass finely balanced by electron degeneracy pressure. This delicate state ensures that it neither collapses nor expands further, providing a stable core for any planetary systems orbiting it. The surface temperature of these cooling stars can drop below 13,000 Kelvin after billions of years, making them some of the oldest witnesses to our universe's history. Yet their role extends far beyond mere observation. They are vital custodians of the cosmic order, ensuring long-term stability within star systems like our own. Imagine a white dwarf with a mass equivalent to the Sun, but condensed into an object just slightly larger than Earth. This extraordinary density is possible because each cubic centimeter contains roughly 5 grams of matter, equivalent to the weight of a small car on Earth's surface. Despite their cooling, these stars maintain structural integrity due to quantum mechanical forces that prevent further collapse. In human terms, this resilience translates into lifespans measured in trillions of years for some white dwarfs, far exceeding the current age of the universe. This longevity underscores why they are essential for supporting stable planetary systems over cosmic timescales. White dwarfs contribute significantly to the overall stability of their respective star systems by maintaining low mass loss rates throughout their cooling phase. Unlike more massive stars, which shed considerable amounts of material during late-stage stellar evolution, white dwarfs conserve almost all of their initial mass. This conservation is crucial for planetary systems, as it ensures a steady gravitational environment conducive to life-friendly conditions on orbiting planets. The constancy of a white dwarf's gravitational influence allows planets to maintain stable orbits and climates over billions of years, fostering the potential for long-term habitability. Additionally, the low luminosity of cooling white dwarfs means that they do not significantly alter their planetary system's thermal environments, preserving conditions favorable for life. The crystalline structure within cooling white dwarfs is remarkable, with carbon and oxygen atoms arranged in a lattice similar to that found in diamonds. This solid-state matter formation occurs as temperatures drop below 10 million Kelvin, causing ions and electrons to freeze into place, creating what scientists call degenerate matter. Surprisingly, despite the extreme density of degenerate matter, it can support vast amounts of mass without collapsing under its own gravity. This property allows white dwarfs to cool for billions of years without exploding or collapsing catastrophically, ensuring their stability over vast cosmic timescales. Some white dwarfs in binary systems emit X-rays due to accretion processes, even though they are cooling and have surface temperatures far below 10,000 Kelvin. This occurs when material from a companion star falls onto the white dwarf's surface at high speeds, generating intense heat through friction and compression. The resulting X-ray emissions are faint but detectable by sensitive space telescopes like Chandra or XMM Newton. These observations provide crucial insights into stellar evolution and binary interactions in our galaxy. For astronomers, these emissions offer a window into the complex dynamics of star systems that might otherwise remain hidden from view. Astronomers have discovered white dwarfs older than 10 billion years, indicating they formed during the early stages of galactic formation, when the universe was less than 2 billion years old. These ancient stars provide valuable data on how stellar remnants evolve over time and offer clues about the initial conditions of our universe. Their enduring presence throughout cosmic history supports the notion that stable star systems are a fundamental feature of our galaxy's architecture. Understanding these relics not only enriches our knowledge of stellar evolution, but also sheds light on the potential for long-lasting planetary systems across the cosmos. At the boundary where interstellar gas clouds and cooling white dwarfs meet, a subtle dance begins as hydrogen and helium molecules accrete onto the surface of these dying stars. This process marks a final cosmic nourishment for these cooling remnants as they prepare to enter a phase of total darkness. Each molecule carries within it an ancient history, expelled from previous generations of stars in stellar nurseries. These interactions between gas clouds and white dwarfs create ripples that traverse vast distances across the cosmos. While the disturbances are minuscule on human scales, mere fractions of a degree in temperature change, they ripple through space like faint signals. In contrast, our understanding of gravity spans from the subatomic to the cosmic. Each disturbance is a testament to the interconnectedness of celestial objects. Inside these cooling stars, as matter settles onto their surfaces, it undergoes remarkable transformation. Hydrogen and helium are compressed under incredible pressure, reaching conditions not found elsewhere in the universe outside neutron stars or black holes. This compression changes the very nature of these elements, crystallizing them into structures that resemble perfect diamonds on Earth. Yet, unlike terrestrial gems, these crystals form under relentless gravity without ever being exposed to sunlight. Over time, as more material accumulates on the white dwarf surface, it sets off a series of nuclear reactions in localized regions known as accretion disks. These reactions generate X-rays that can be detected by instruments on Earth, providing insights into the processes at play near its surface. The energy emitted is paradoxical. While the star itself has long ceased to produce energy through fusion, these brief bursts of activity offer a glimpse into the complex dynamics of stellar evolution. The oldest known white dwarfs are around 10.5 billion years old, older than our solar system by nearly 4 billion years. These ancient stars have cooled significantly, with surface temperatures dropping below 3000 Kelvin. Their cooling process is not uniform. Some regions may still emit faint X-rays due to accretion events from binary companions. This variability highlights the complexity of their final stages. The density of these cooling white dwarfs is extraordinary, equivalent to placing 5.5 million kilograms in a teaspoonful on Earth. Despite this, they maintain structural stability through electron degeneracy pressure, which prevents further collapse beyond a specific size limit set by the Chandrasekhar mass of 1.4 solar masses. This equilibrium ensures that these stars neither expand nor contract further, preserving their form for eons. As we consider the fate of these cooling white dwarfs, it becomes apparent that they will eventually cease to emit any detectable radiation, becoming what astronomers call black or cold white dwarfs. These remnants are not entirely devoid of activity. Residual heat from accretion events may still cause slight temperature variations on their surfaces. Yet over time, even this minimal warmth fades away. In the vastness of space, Cooling white dwarfs and interstellar gas clouds coexist in a delicate equilibrium that spans cosmic timescales. Their interactions offer a unique window into stellar evolution and the intricate balance between accretion and cooling processes. In the vacuum of space, where sound waves cannot propagate due to the absence of molecules, an alien species navigates using advanced sonar technology. This equipment detects subtle changes in acoustic pressure caused by the faint radiation emitted from cooling white dwarfs. The fluctuations are minute but crucial for precise navigation through the void. The oldest known white dwarf is approximately 10.5 billion years old, predating our solar system by nearly 4 billion years. It has cooled to below 3,000 Kelvin after burning out its nuclear fuel and now radiates thermal photons into space. For these alien navigators, each pressure change detected offers a detailed record of the star's cooling process. The variations are akin to tuning an instrument, ensuring their sonar remains perfectly calibrated as they travel through deep space. The white dwarf's crystalline structure, primarily composed of carbon and oxygen, contributes to these subtle fluctuations in acoustic pressure. This solid state means it no longer supports nuclear fusion, but instead radiates heat slowly over billions of years. The alien navigators use this information not just for navigation, but also to understand the vast timeline of stellar evolution in their cosmic neighborhood. Each detection is a snapshot of its cooling journey, revealing the star's transition from an active burning phase to its current state. Despite being incredibly dense, packing as much mass as our Sun into a sphere about 8,000 kilometers across, the white dwarf emits very little sound pressure due to the vacuum. However, for these alien navigators, the minute changes in pressure are enough to provide crucial data. The cooling process of this ancient star is part of a larger cosmic cycle where stars evolve and eventually become remnants like white dwarfs. As they navigate through space, the aliens encounter numerous other white dwarfs scattered across the universe. Each one offers unique acoustic signatures, reflecting its specific age and evolutionary stage. These pressure changes provide a continuous stream of information about stellar histories, from the fiery birth of these stars to their eventual cooling into cold embers floating in the vastness of space. This navigation technique allows them to map out regions of star formation, ancient clusters, and areas where new planets might be forming around these cool remnants. The pressure changes detected by the sonar also reveal unexpected connections between stellar evolution and cosmic time itself. The white dwarf's cooling process is a testament to the universe's age, with each photon emitted stretching across billions of years of expansion. For these navigators, this ancient radiation serves as both a guide and a reminder of the vast timescales involved in the life cycles of stars. Their sonar technology captures not just points in space, but moments frozen in time, offering insights into the universe's grand narrative. The alien navigators also notice that certain white dwarfs emit X-rays if they accrete matter from a binary companion, despite being cool remnants of dead stars. These X-ray emissions are generated when material falls onto the surface of the white dwarf at extremely high velocities, heating it to temperatures as high as 30,000 Kelvin. This phenomenon provides an intriguing contrast to the general cooling trend of these objects. For the navigators, these X-rays serve not only as a marker of accretion activity, but also as a reminder that even in death, some stars continue to engage in dynamic processes. The pressure changes detected from these X-ray emitting white dwarfs are more pronounced and complex than those from their cooler counterparts. The variations in acoustic pressure can reveal the rate at which material is being accreted and the temperature fluctuations on the star's surface. This data offers a glimpse into the intricate dance between the white dwarf and its companion, where gravity pulls matter inward while radiation pushes it outward. For the alien navigators, these subtle shifts in pressure are like reading the heartbeat of a dying star, revealing both its past interactions and its current state. Moreover, the presence of X-ray emissions from accreting white dwarfs introduces an element of unpredictability into their navigation. While most white dwarfs emit thermal radiation uniformly, those with binary companions can exhibit sudden bursts or continuous variations in pressure. This complexity challenges the navigators to refine their sonar algorithms constantly, ensuring they account for these dynamic changes. The universe, it seems, even in its quieter moments, offers a rich tapestry of phenomena for those who listen closely. Each detection of these pressure changes paints a picture not only of individual stars, but also of entire systems. For instance, the pattern of X-ray emissions can indicate whether the companion star is a red giant or a main sequence star, offering clues about the system's age and evolutionary stage. The alien navigators use this information to map out regions where stellar. In the quiet expanse of space, a white dwarf begins its long journey from a hot blue star to a cool red ember. The surface temperature of this particular white dwarf is currently around 13,000 Kelvin, slowly cooling over billions of years toward a final equilibrium below 3,000 Kelvin. This transition marks the end of nuclear fusion within the core, as temperatures drop below 10 million Kelvin, halting the process that once powered its luminosity. Each photon emitted from the surface carries information about this star's journey through time, stretching across vast distances to reach us. The cooling process is a slow but steady reduction in temperature over cosmic epochs, marking significant changes in the star's physical properties. As the white dwarf cools, its crystalline core forms structures similar to diamonds, solidifying into an enduring state. This transformation from gas to solid marks the end of active nuclear processes within the star. The cooling process is a slow but steady reduction in temperature over time, with each stage marking significant changes in the star's physical properties. Despite their cool state, some white dwarfs can emit X-rays if they accrete matter from nearby companions. These localized regions reach temperatures as high as 30,000 Kelvin, illustrating the complexity of their cooling process. The oldest known white dwarf is nearly 4 billion years older than Earth itself, predating our solar system by billions of years. This ancient remnant provides insights into cosmic history and the formation of galaxies. In this environment, sound cannot propagate due to the vacuum, but each photon emitted from a white dwarf carries information about its journey through billions of years. The cooling process marks the end of nuclear fusion within its core, as temperatures drop below 10 million Kelvin, halting the process that once powered its luminosity. Each photon stretches across 10,000 light years, carrying with it the history of this star's evolution. This radiation is a faint echo of what was once an intense stellar furnace, now cooling to a mere shadow of its former self. The white dwarf's surface temperature will continue to decrease over time, eventually reaching a point where even X-ray emissions cease. The heat transfer in this vacuum environment occurs solely through radiation, with no conduction or convection possible due to the absence of matter. Over time, the white dwarf's luminosity diminishes steadily, eventually fading from view as its light stretches thin across billions of years. This cooling process is a slow but steady reduction in temperature over cosmic epochs, marking significant changes in the star's physical properties. Despite their cool state, some white dwarfs can emit X-rays if they accrete matter from nearby companions. These localized regions reach temperatures as high as 30,000 Kelvin, illustrating the complexity of their cooling process. This ancient remnant provides insights into cosmic history and the formation of galaxies. The crystalline structure within a white dwarf is composed primarily of carbon and oxygen, arranged in a lattice similar to diamonds. This solid core forms under immense pressure from electron degeneracy, preventing further collapse beyond its stable size. The density of this material is extraordinary. A teaspoonful would weigh about 5 million kilograms on Earth. As the white dwarf cools, these crystalline structures slowly rearrange themselves into more stable configurations, a process that can take billions of years to complete. This transformation from gas to solid marks the end of active nuclear processes within the star, leaving behind a remnant that will continue to cool for eons. In the depths of space, where stars have long since exhausted their nuclear fuel and cooled into embers, X-ray telescopes detect a faint glow emanating from accretion disks surrounding white dwarfs. This process marks a final cosmic nourishment for these cooling remnants as they prepare to enter a phase of total darkness. The iron in your blood was forged in stars that died before our sun existed, and now we observe the remains of those ancient stellar furnaces. These white dwarfs are relics of a time when the universe was younger and more energetic, bearing witness to the passage of cosmic eons. Each one is a testament to the relentless march of time across billions of years. Surprisingly, some white dwarfs can experience brief bursts of activity known as dwarf nova outbursts, where they suddenly brighten by thousands of times their normal luminosity before dimming again. This unexpected behavior reveals that even in death, these stars can still exhibit dynamic and energetic phenomena. Before it became a cooling white dwarf, this star was part of a vibrant cluster of stars that seeded galaxy formation through supernova explosions. These clusters were not merely collections of stars, but dynamic entities where stellar interactions played out over billions of years. Each supernova explosion within these clusters scattered heavy elements across regions up to 100 parsecs away, enriching the interstellar medium with iron, silicon, and oxygen, elements essential for planet formation. The energy released in a single supernova can momentarily outshine an entire galaxy, yet it is just one event in a cycle that repeats countless times throughout cosmic history. In these clusters, stars formed from clouds of gas enriched by previous generations of stellar explosions. This recycling process ensures that each new generation of stars contains more heavy elements than the last. The oldest known white dwarf, at around 13.8 billion years old, predates our solar system and is a relic of one such ancient cluster. Its composition, primarily carbon and oxygen in a crystalline structure, reflects its origins as part of a star that once burned brightly before collapsing into this cold remnant. The density of a teaspoonful of white dwarf material would weigh about 5.6 million kilograms on Earth, illustrating the extreme compression achieved during stellar collapse. The cooling process of these white dwarfs is gradual and precise, with temperatures dropping from over 13,000 Kelvin to below 3,000 Kelvin over billions of years. This slow decline in temperature allows astronomers to use white dwarfs as cosmic clocks, providing age estimates for star clusters and galaxies. The oldest known white dwarf has been cooling for nearly 4 billion years longer than our solar system has existed. Its crystalline structure is akin to that found in diamonds on Earth, yet it spans the size of a planet while containing mass comparable to our Sun. This paradoxical combination of small size and immense density underscores the unique nature of these stellar remnants. An unexpected twist in this cooling process is that some white dwarfs can experience thermal relaxation oscillations, where their temperature fluctuates slightly before settling into a stable state. Before becoming white dwarfs, many stars were part of binary systems where they interacted closely with companion stars. Some of these interactions led to accretion events, where material from a companion star fell onto the surface of the white dwarf. This process can generate X-rays, even in objects that are otherwise cool and dim. The faint glow detected by X-ray telescopes reveals the ongoing activity of these ancient stars, despite their apparent dormancy. Accretion disks around white dwarfs provide evidence of past stellar interactions and offer insights into the complex dynamics within star clusters. The formation of galaxies is intimately linked to the life cycles of stars within them. Supernova explosions from massive stars not only enrich the interstellar medium with heavy elements, but also trigger new rounds of star formation by compressing nearby gas clouds. This cycle of stellar birth, death, and rebirth has been ongoing for billions of years, shaping the structure and evolution of galaxies. The oldest white dwarfs are relics of this process, remnants of stars that once contributed to the enrichment of their host galaxies' interstellar medium. Their presence serves as a reminder of the continuous recycling of matter throughout cosmic history. As we observe cooling white dwarfs today, we are witnessing the final stages of stellar evolution for many ancient stars. These embers floating in space represent the end point of billions of years of nuclear fusion and subsequent collapse. The temperature of these objects continues to drop as they radiate away their residual heat into the vastness of space. Over time, they will eventually cool below detectable levels, becoming dark stellar remnants that no longer emit significant radiation. This process highlights the transient nature of stars and underscores the enduring cycle of cosmic change that has shaped our universe. The cooling of white dwarfs is a process that unfolds over billions of years, gradually releasing heavy elements into the interstellar medium. These remnants of stars that have exhausted their nuclear fuel are crucial for galactic chemistry, enriching space with materials essential for new star formation. A typical white dwarf takes around 13.8 billion years to cool below 3000 Kelvin, a period during which it sheds its outer layers, contributing to the cosmic recycling of elements like carbon and oxygen. This process is not uniform. Some white dwarfs can take up to 8 billion years to reach this temperature, depending on their initial mass and composition. As these cooling stars release heavy elements into space, they play a vital role in seeding future star systems with the necessary building blocks for life. The iron in your blood was once part of a supernova that occurred before our sun's formation, illustrating how ancient stellar processes shape the universe we inhabit today. These white dwarfs are not merely passive objects. Their cooling process is dynamic, involving complex interactions between radiation and the vacuum of space. This interaction ensures that heat transfer occurs solely through radiation, as there are no molecules to facilitate conduction or convection in the cosmic void. The crystalline structure within a white dwarf's core is similar to that found in diamonds on Earth, composed primarily of carbon and oxygen. Despite their small size, similar to Earth's radius of about 8,000 kilometers, white dwarfs contain masses comparable to our Sun. This extreme density results from electron degeneracy pressure, which stabilizes the star against further collapse once it has exhausted its nuclear fuel. Surprisingly, some white dwarfs can experience a reverse process called crystallization, where their solid cores grow over time. This phenomenon not only cools them, but also changes their internal structure, potentially affecting how they interact with surrounding space. In binary systems, white dwarfs can accrete matter from their companions, leading to the emission of X-rays despite their cool temperatures. These emissions, detectable by Earth-based instruments, offer valuable insights into these ancient stellar remnants. The iron and oxygen within these white dwarfs were once part of larger star systems, contributing to the creation of new worlds through their eventual dispersion into space. This process highlights how the death of one generation of stars supports the birth of another, driving the ongoing cycle of cosmic evolution. The oldest known white dwarf is approximately 13.7 billion years old, predating our solar system by nearly 4 billion years. These ancient relics provide a glimpse into the early universe's chemical composition, preserving a history of stellar evolution that spans billions of years. As they cool, these stars release heavy elements into the interstellar medium, enriching it with materials essential for future star formation. This process is crucial for galactic chemistry, ensuring that new generations of stars have access to the same building blocks that once created our Sun. As white dwarfs continue their slow journey toward total darkness, they play a vital role in the distribution of heavy elements across galaxies. Their cooling process, which spans billions of years, ensures that future stars and planets are formed with the same materials that once created our own solar system. This intricate process highlights the interconnectedness of stars throughout the universe, where the remnants of one generation fuel the next, driving the formation of new star systems over cosmic timescales. Gravitational waves from binary white dwarf mergers offer a unique window into the internal structure and dynamics of these ancient stellar remnants. These ripples in spacetime are detectable when two white dwarfs orbit each other closely enough to begin emitting gravitational radiation. This process is akin to the faint hum of distant machinery, though no sound can travel through the vacuum of space. Each merger event provides precise measurements of the star's masses and internal structures. The signal from these waves allows astronomers to map out populations of merging white dwarfs across different regions of the Milky Way. By analyzing the frequency and intensity of these signals, researchers gain insights into how binary systems evolve over time. Some systems may approach each other so closely that they eventually merge, releasing energy equivalent to 1044 joules in a cosmic dance. The Chandrasekhar limit, precisely 1.4 solar masses, acts as a threshold beyond which a star cannot form a stable white dwarf. Should two merging white dwarfs exceed this mass, they could trigger a Type I supernova. This explosion would release an extraordinary amount of energy and heavy elements into space, enriching the interstellar medium for future generations of stars. The detection of gravitational waves helps astronomers predict such events with greater accuracy. Binary white dwarf mergers also provide valuable data on the distribution and properties of these systems within our galaxy. By studying the distances between merging pairs, scientists can gather information about how the rate of cosmic expansion has changed over time. This contributes to our understanding of dark energy, which is thought to be responsible for the accelerated expansion of the universe. The precise measurements from gravitational waves offer insights into the physics of extreme environments within binary white dwarfs. These systems provide a unique opportunity to explore electron degeneracy pressure and the behavior of matter under conditions not found elsewhere in nature. The data helps refine models of stellar evolution, offering deeper understanding of how stars like our Sun will eventually end their lives. Each gravitational wave event detected from merging white dwarfs is more than just an astronomical observation. It's a snapshot of cosmic history. These signals reveal the intricate details of stellar evolution and the processes that shape galaxies over billions of years. As we continue to detect these waves, our understanding of the universe will expand, revealing new mysteries and offering deeper insights into the origins and fate of stars like our own. Gravitational wave detectors such as LIGO and Virgo are exquisitely sensitive instruments, capable of registering minute distortions in spacetime that occur when two white dwarfs merge. These ripples are so subtle that they stretch or squeeze the detector's mirrors by a fraction of the width of an atomic nucleus. This level of precision allows scientists to study not only the final moments of these mergers, but also the long history leading up to them. The internal structure of merging white dwarfs is particularly intriguing. As two stars approach each other, their gravitational fields begin to interact more strongly, causing tidal forces that can deform and redistribute matter between them. This process gradually synchronizes their rotation rates until they eventually merge into a single entity. The resulting object may either settle into a stable configuration or collapse further if it exceeds the Chandrasekhar limit. Understanding these processes helps us comprehend how binary systems evolve over cosmic timescales. Some white dwarfs take billions of years to cool down completely after their formation, during which time they can interact with other stars in complex ways. These interactions can lead to accretion events or even mergers that alter the fate and properties of both objects involved. Moreover, these gravitational wave signals provide a direct measurement of the speed at which spacetime itself is warped by massive objects. This information is crucial for testing Einstein's theory of general relativity under extreme conditions where gravity is strongest. Such tests not only validate our current understanding, but also open up new avenues for exploring fundamental physics in the most challenging environments known to us. Each binary white dwarf merger represents a unique moment in cosmic history, offering insights into stellar evolution and galactic dynamics. By studying these events through gravitational waves, astronomers gain valuable data that can be used to refine models of star formation, stellar death, and the large-scale structure of galaxies. These observations continue to deepen our appreciation for the intricate processes shaping the universe around us. The cooling white dwarf drifts in space, its surface temperature slowly dropping below 3000 Kelvin. This ancient remnant of a once vibrant star now emits faint thermal radiation as it cools over billions of years. Each photon from this dying ember travels across vast distances, stretching into longer wavelengths by the expansion of space itself. In contrast, nearby young stars blaze with intense light, their cores fusing hydrogen at temperatures exceeding 15,000 Kelvin. As the white dwarf continues to cool, its crystalline structure remains stable, supported by electron degeneracy pressure. This equilibrium prevents further compression beyond its current size, maintaining a radius similar to Earth's despite containing mass comparable to our Sun. Meanwhile, these young stars are still accumulating mass and energy, preparing for their eventual transformations into red giants or supernovae. The stark difference in luminosity between the cooling white dwarf and the vibrant young stars underscores the vast range of stellar life cycles. The process by which a white dwarf cools is an intricate one, involving the gradual release of residual heat through radiation. Over time, this cooling star will grow dimmer, eventually becoming too faint to be detected by most telescopes. In contrast, nearby young stars continue their energetic phase, radiating energy at a rate that defines their futures. These youthful stars are part of a galactic nursery, where new stellar systems form and evolve over cosmic timescales. The cooling white dwarf's crystalline structure is composed primarily of carbon and oxygen, arranged in a diamond-like lattice. This arrangement provides the necessary stability to prevent further collapse under its immense gravity. Meanwhile, young stars nearby are still in the process of forming planetary systems, their gravitational fields attracting dust and gas from surrounding clouds. The contrast between these two stages of stellar evolution highlights the diverse processes that shape galaxies. While the cooling white dwarf grows dimmer with each passing century, it remains a stable remnant of its former glory. Its crystalline structure ensures it neither collapses nor expands further, providing a lasting anchor for any planetary systems that may orbit it. In contrast, young stars nearby are still accumulating mass and energy, preparing for their eventual transformations into red giants or supernovae. These youthful stars are part of a galactic nursery, where new stellar systems form and evolve over cosmic timescales. The cooling white dwarf represents one end of the stellar life cycle, marking the final stages after billions of years of nuclear fusion. In contrast, nearby young stars continue their energetic phase, radiating energy at an intense pace that will last for millions or billions of years. The vibrant lights of these youthful stars offer a stark contrast to the fading glow of the cooling white dwarf, highlighting the different stages of stellar evolution across the universe. The cooling white dwarf surface temperature steadily decreases, now below 3000 Kelvin, marking a phase where it emits less and less thermal radiation into the void. Nearby young stars, in stark contrast, emit light so intense that their energy output can be detected across vast cosmic distances. These youthful stars are not just luminous, they are also dynamic, with variable brightness due to magnetic activity or stellar flares, adding a flickering element to their otherwise steady glow. As the white dwarf cools further, its rate of radiating heat slows down dramatically. The star's luminosity diminishes, making it increasingly difficult for even advanced telescopes to detect beyond certain distances. Meanwhile, young stars nearby are in the midst of nuclear fusion, converting hydrogen into helium with explosive vigor. This process releases vast amounts of energy, visible as bright light and sometimes X-rays from their active surfaces. The white dwarf's gradual cooling is a testament to the long-term stability of electron degeneracy pressure, which prevents further collapse despite immense gravitational forces. In contrast, young stars are still in the throbbing phase of their lives, pulsating with magnetic fields and stellar winds that sculpt interstellar clouds into new star-forming regions. This dynamic interplay between cooling remnants and vibrant newborns illustrates the diverse stages of stellar evolution across cosmic time. The cooling white dwarf surface temperature steadily decreases, now below 3000 Kelvin, marking a phase where it emits less and less thermal radiation into the void. Nearby young stars, in stark contrast, emit light so intense that their energy output can be detected across vast cosmic distances. These youthful stars are not just luminous, they are also dynamic, with variable brightness due to magnetic activity or stellar flares, adding a flickering element to their otherwise steady glow. The cooling white dwarf surface temperature steadily decreases, now below 3000 Kelvin, marking a phase where it emits less and less thermal radiation into the void. Nearby young stars, in stark contrast, emit light so. The hypothetical planet in our scenario orbits close to its white dwarf sun, receiving a faint but consistent illumination. This light is much dimmer than what we experience on Earth, yet it remains stable across time, offering an unchanging glow for potential inhabitants. The surface temperature near the star fluctuates minimally due to its low variability, creating conditions where simple organic molecules can persist without freezing or evaporating. The light spectrum emitted by this cooling star is also critical, as it provides just enough energy to drive basic chemical reactions essential for life's emergence. Near the white dwarf surface, thermal radiation plays a key role in warming any exposed materials, but sound cannot travel through this vacuum. Any potential life forms would need to develop alternative means of communication or sensation, relying on vibrations or light signals rather than sound waves. This silent world, bathed in faint red light, offers an environment that is both serene and alien. The cooling process of the white dwarf ensures a steady supply of thermal radiation for billions more years, providing a stable environment for any emerging life to adapt and evolve. The gravity on this hypothetical planet would be significantly stronger than what we experience on Earth, approximately 24 times greater due to the high density of its star. Were it possible for humans to stand here, every step would feel like lifting heavy weights, and movement would require considerable effort. The intense gravitational pull is not only because of the star's high density, but also its relatively small size. This creates an environment where weight becomes a significant factor in daily life, influencing everything from movement to the design of structures. The faint illumination from the white dwarf contrasts with the light of distant galaxies visible in the night sky. While the central star provides a constant glow, the light from other stars is stretched into longer wavelengths due to the expansion of space itself. This phenomenon, known as redshift, means that even nearby stars appear dimmer and redder than they would closer to home. The cooling white dwarf has a mass comparable to our Sun, but with a radius similar to Earth's, creating an extraordinary density. This makes it one of the densest objects in the universe. Despite its stability, this planet presents an unexpected challenge. The faint red light from the white dwarf can cause visual fatigue over time. Prolonged exposure may lead to temporary color blindness or difficulty distinguishing between shades of red and green. This could affect how potential inhabitants perceive their surroundings, potentially leading to unique adaptations in vision or behavior. The cooling process of the white dwarf ensures a steady supply of thermal radiation for billions more years, providing a stable environment for any emerging life to adapt and evolve. The surface temperature near the star fluctuates minimally due to its low variability, creating conditions where simple organic molecules can persist without freezing or evaporating. This stability contrasts with the more variable conditions found closer to larger stars or planets orbiting them. Any potential life forms would need to develop alternative means of communication or sensation, relying on vibrations or light signals rather than sound waves. In the heart of a white dwarf, electrons press against one another with a force that defies classical physics, maintaining equilibrium through electron degeneracy pressure. This pressure is so immense it prevents further collapse beyond the star's current size, even as its core cools over billions of years. Each cubic centimeter of material within this stellar remnant can weigh up to 10 tons on Earth, a testament to the extraordinary density achieved in these cooling stars. In contrast, neutron stars, which form from more massive progenitors, experience pressures that are orders of magnitude higher, reaching as much as 10 times the pressure at the center of a white dwarf. This extreme compression is what allows neutrons to exist in such close proximity, forming a superfluid state where particles behave like waves. The core of a cooling white dwarf maintains an internal temperature below 10 million Kelvin, insufficient for nuclear fusion, but sufficient to keep electrons in their degenerate state. Meanwhile, neutron stars can reach temperatures up to 500 billion Kelvin at their cores, enabling the formation of exotic states of matter like quark-gluon plasma. This stark difference in core temperatures underscores the varying stages of stellar evolution and the diverse outcomes that can arise from a star's life cycle. For instance, while white dwarfs cool over time without significant further change, neutron stars continue to radiate energy through processes such as magnetic field decay and particle emission, gradually losing their heat. Imagine standing on Earth with a scale capable of measuring pressure. The deepest ocean trenches experience pressures around 10,000 atmospheres, yet this pales in comparison to the pressures within white dwarfs and neutron stars. In fact, the pressure at the center of a typical neutron star is approximately 4x 1035 Pascal, equivalent to compressing Earth's entire atmosphere into the volume of a single grain of sand. This immense pressure is what allows neutrons to exist in such close proximity, forming a superfluid state where particles behave like waves, defying classical physics and providing insights into quantum mechanics on an astronomical scale. White dwarfs cool over time due to radiation from their surfaces, gradually reaching temperatures below 3000 Kelvin after approximately 10 billion years. In contrast, neutron stars emit energy through processes such as magnetic field decay and particle emission, slowly cooling down over trillions of years. This difference in cooling mechanisms reflects the distinct evolutionary paths these stellar remnants follow. While white dwarfs eventually fade into darkness, neutron stars maintain detectable activity for much longer periods, offering astronomers valuable insights into the physics of extreme environments. However, an unexpected twist is that some white dwarfs can experience a brief resurgence of nuclear fusion late in their cooling phase, known as a late thermal pulse, which temporarily brightens them before they resume their gradual dimming. The crystalline structure within a white dwarf's core is similar to that found in diamonds on Earth, with carbon and oxygen atoms arranged in a lattice. This rigid arrangement contributes to the stability of electron degeneracy pressure, preventing further collapse beyond the star's current size. In neutron stars, however, the extreme pressures force neutrons into an even more compact state, where they overlap quantum mechanically. This superfluid state allows for unique phenomena like glitching pulsars, where sudden changes in rotation rates occur due to internal adjustments within the star. As white dwarfs cool and radiate their remaining heat into space, they gradually approach a state of thermal equilibrium with their surroundings. Over time, these cooling stars will emit less radiation, eventually becoming virtually invisible against the cosmic background. In contrast, neutron stars continue to shine through processes like magnetic field decay and particle emission, maintaining detectable activity for trillions of years. This difference highlights the enduring nature of neutron stars compared to the eventual silence of white dwarfs in the vastness of space. Cooling white dwarfs exhibit a remarkable range of cooling rates influenced by their initial mass and composition, creating a spectrum of thermal histories across space. The core temperature of these stars drops from thousands of Kelvin to below 3,000 Kelvin over billions of years, with the exact timeline depending on factors like the star's starting mass. A white dwarf born from a more massive progenitor will cool faster than one formed from a less massive star. This cooling process is akin to watching paint dry at cosmic scales, slow and steady. The Chandrasekhar limit plays a pivotal role in determining this variability, setting a precise threshold of 1.4 solar masses beyond which a star cannot form a stable white dwarf. Stars that exceed this limit collapse into neutron stars or black holes instead. For those below the limit, electron degeneracy pressure halts further gravitational contraction, stabilizing them at sizes similar to Earth's radius, but with mass comparable to the Sun. This stabilization process is crucial for understanding how these remnants maintain their structure over time. White dwarfs are not static objects. They continue to evolve through crystallization as they cool. The carbon and oxygen within their cores gradually solidify into a crystalline lattice, similar to diamond structures on Earth. This transformation occurs over billions of years, with the cooling process slowing down significantly once this phase begins. For instance, a white dwarf that has already cooled for 10 billion years might take another 8 billion years to reach its final equilibrium temperature. The age of these cooling stars provides astronomers with valuable insights into stellar evolution and galactic history. The oldest known white dwarf is approximately 10.5 billion years old, predating our solar system by nearly 4 billion years. This ancient relic offers a window into the early universe, where star formation was more frequent and diverse. By studying such objects, scientists can reconstruct the conditions under which these stars formed and evolved. In binary systems, white dwarfs may accrete matter from their companions, leading to unexpected thermal emissions. Some of these cooling remnants emit X-rays despite being cool, with temperatures reaching as low as 30,000 Kelvin in certain cases. This phenomenon occurs when material falls onto the surface of the white dwarf, generating intense heat through friction and compression. These X-ray emissions provide a unique signature for identifying accreting white dwarfs among other cooling stars. As white dwarfs cool over time, they release heavy elements into the interstellar medium, contributing to galactic chemistry. The iron in your blood was forged in a star that died before our sun existed, and these remnants continue to enrich space with materials essential for new star formation. This cycle of stellar birth, death, and rebirth underscores the interconnectedness of cosmic processes across vast timescales. The cooling rates of white dwarfs are not uniform. They vary significantly based on their initial mass and composition. Heavier white dwarfs, formed from larger progenitor stars, cool more slowly due to their greater thermal inertia. This means that a white dwarf with twice the mass of another will take longer to reach the same temperature during its cooling process. Conversely, lighter white dwarfs cool more rapidly, often reaching temperatures below 3000 Kelvin in just over 10 billion years. This variation is crucial for understanding the diverse lifespans and evolutionary paths of these stellar remnants. The crystallization process within white dwarfs introduces an interesting layer of complexity to their cooling dynamics. As the core cools and solidifies into a diamond-like structure, it can actually slow down the overall cooling rate due to reduced heat conductivity in the solid state compared to when the material was fluid. This phenomenon is akin to how a metal spoon feels cooler to touch than its wooden handle. Solid materials conduct heat less efficiently. Despite this slowdown, crystallization also marks an important phase transition that can be observed through changes in the white dwarf's luminosity and spectral characteristics. Each cooling white dwarf represents a unique snapshot of stellar evolution, offering insights into the conditions under which stars formed billions of years ago. By studying these objects, astronomers can trace back the chemical enrichment history of galaxies, revealing how elements heavier than hydrogen and helium were distributed throughout space over time. This information is vital for understanding the formation and development of planetary systems like our own, where heavy elements are key ingredients for rocky planets and potential life-supporting environments. White dwarfs also serve as cosmic thermometers, allowing scientists to measure the expansion rate of the universe through their redshifted light. As these stars cool, their emitted photons are stretched by the expanding fabric of space-time, shifting towards longer wavelengths. This effect provides a precise method for determining distances and ages across vast cosmological scales, offering a glimpse into the grand tapestry of cosmic history. In the deep future, when all stars have cooled into black dwarfs, leaving behind an empty universe where only dark matter remains dominant, a profound transformation will occur across the cosmos. Each cooling white dwarf, now at temperatures below 3000 Kelvin, continues its slow journey toward equilibrium. This process unfolds over trillions of years, with some taking up to 10 billion years just to cool down after their formation. The cooling rate varies significantly depending on a white dwarf's initial mass and composition. For instance, heavier white dwarfs cool more slowly due to their larger thermal reservoirs. These remnants are composed primarily of carbon and oxygen in a crystalline structure, similar to diamonds. Imagine an object the size of Earth containing as much mass as our Sun. This extreme density is found within these cooling stars. In this environment where space stretches over 93 billion light-years, white dwarfs emit faint thermal radiation, their energy slowly dissipating into space through a process known as blackbody radiation. This method of cooling contrasts with our everyday experience on Earth, where objects cool by exchanging heat with their surroundings. In the vacuum of space, however, there are no such exchanges. Instead, radiation is the sole method of energy transport. Over time, these cooling white dwarfs will emit less and less light until they become virtually invisible. The universe in this deep future will be an almost silent expanse, with sound unable to propagate due to the lack of molecules. Despite their cold temperatures, some white dwarfs can still emit X-rays if they accrete matter from a binary companion. This phenomenon occurs when material falls onto the surface of these stars, briefly heating it to tens of thousands of Kelvin, far hotter than its overall temperature. As we peer into this distant future, we encounter an intriguing paradox. While the universe expands and cools, the cooling white dwarfs themselves are remnants of past stellar activity. These ancient embers hold within them the history of star formation in our galaxy. The oldest known white dwarf is around 10.5 billion years old, older than our solar system by nearly 4 billion years, bearing witness to epochs long since past. In this empty universe dominated by dark matter, the cooling process continues until all white dwarfs reach their final state as black dwarfs, stellar remnants that no longer emit any radiation. This transition marks a cessation of nuclear activity and thermal emission, leaving behind objects that are effectively invisible in the electromagnetic spectrum. The universe will then be populated solely by these cold relics and dark matter, a stark contrast to its current vibrant state, filled with stars and galaxies. In this future epoch, the black dwarfs will have radii similar to Earth's, about 8,000 kilometers, but contain masses comparable to our Sun. This extraordinary density is due to the intense pressure exerted by electrons in their cores, preventing further collapse beyond a certain point. Each cubic centimeter of these objects would weigh approximately 5 tons on Earth, illustrating just how compact and dense they have become through billions of years of cooling. When all stars have cooled into black dwarfs, the universe will be an unimaginably quiet place, devoid of light from active stars or galaxies. The expansion of space itself will continue to stretch any remaining photons emitted by these ancient remnants, diluting their energy across vast distances. This process ensures that even if a white dwarf were emitting radiation at its peak, it would eventually become undetectable against the backdrop of dark space. In this deep future, the universe will have aged to unimaginable proportions, perhaps trillions of years beyond our current understanding of time. By then, even the black dwarfs themselves may no longer exist in their current form, as they gradually break down into fundamental particles over incomprehensibly long timescales. The remnants of stars that once illuminated the cosmos will have faded entirely, leaving behind a universe dominated by dark matter and the vacuum of space. While all white dwarfs eventually cool to become black dwarfs, some may never reach this final state due to quantum effects. These objects, known as frozen stars, could theoretically hold onto their heat indefinitely, thanks to the peculiar properties of quantum mechanics at extremely low temperatures. This phenomenon introduces an unexpected twist in our understanding of stellar evolution and raises questions about the ultimate fate of these cosmic embers. The cooling process within white dwarfs is a testament to the precision of astrophysical processes across vast scales of time. Each photon emitted represents a tiny fraction of the star's remaining thermal energy, carried away through radiation into the expanding universe. This slow fading. The magnetic fields surrounding some white dwarfs are invisible to human eyes, but play a pivotal role in guiding interstellar gas flows into intricate patterns. These fields can extend for light years, their influence felt across vast distances of space. The strength of these fields is comparable to that found near Earth's surface, yet they exert control over the movement of particles far beyond our reach. Imagine an environment where temperatures plummet below 3000 Kelvin after billions of years. In this cold realm, white dwarfs cool slowly, their surfaces dimming as they release energy into the void. The cooling process is not uniform. Some regions may retain higher temperatures for longer periods, creating hotspots that interact with surrounding magnetic fields in complex ways. These interactions can accelerate particles to near-light speeds, generating X-rays detectable by distant observers. While these white dwarfs are cooling, they continue to influence their surroundings through magnetic fields that guide the flow of interstellar gas. This process is akin to a cosmic conveyor belt, moving material across space in patterns too subtle for human eyes to perceive directly. The iron in your blood was forged in stars similar to these white dwarfs before they cooled, connecting you to the distant past of stellar evolution. The magnetic fields around cooling white dwarfs are not static. They evolve over time as the stars cool down. These fields can undergo reversals, similar to Earth's geomagnetic field, but on much longer timescales. This evolution is a testament to the dynamic nature of these ancient stellar remnants. As a white dwarf continues its journey toward becoming a black dwarf, its magnetic influence gradually weakens until it ultimately fades away. In some cases, white dwarfs can accrete matter from binary companions, leading to X-ray emissions despite their cool temperatures. This process highlights the complexity of interactions within these systems, where even ancient stars continue to engage with their environment in unexpected ways. The accretion disk around such a white dwarf is a dynamic structure, constantly changing as it feeds material onto the star's surface. The cooling of white dwarfs is a process that unfolds over billions of years, gradually releasing heavy elements into the interstellar medium. These remnants enrich space with materials essential for new star formation, playing a crucial role in galactic chemistry. The crystalline structure within these stars, similar to diamonds on Earth, ensures their stability as they cool, maintaining their shape and size through electron degeneracy pressure. The magnetic fields surrounding some white dwarfs are not only powerful, but also highly structured, often featuring complex topologies that can trap particles in intricate patterns. These trapped particles can emit radio waves and other forms of electromagnetic radiation, providing astronomers with indirect evidence of the field's strength and configuration. The patterns created by these interactions are as unique to each white dwarf as a fingerprint, is to an individual human. These magnetic fields can extend for vast distances, sometimes influencing regions far beyond the immediate vicinity of the star itself. In some instances, they can interact with nearby clouds of gas and dust, potentially triggering new cycles of star formation in distant parts of galaxies. This indirect influence underscores the profound impact that even small stellar remnants can have on cosmic processes over immense scales. The magnetic fields of white dwarfs serve as invisible architects, shaping the flow of matter across interstellar space in ways that are both subtle and far-reaching. The strength of these magnetic fields is often a remnant of the star's earlier life stages, when it was still actively fusing hydrogen into helium. As the star evolved and shed its outer layers, the core collapsed under gravity until electron degeneracy pressure stabilized it as a white dwarf. The magnetic field that remains is a relic of this tumultuous history, offering insights into the stars passed through its present-day structure. This connection between the ancient and the contemporary highlights the continuity of cosmic processes across time. The cooling process of these stars also affects their magnetic fields, with temperature changes potentially altering the strength and configuration over billions of years. As a white dwarf cools, it loses energy in the form of radiation, gradually dimming until it reaches thermal equilibrium with its surroundings. This slow fade is not just a visual transformation, but also an energetic one, as the star's internal dynamics shift to accommodate its new state. The magnetic fields that guide interstellar gas flow are thus witnesses to this long-term cooling process, recording the star's gradual transition from luminous ember to cosmic relic. P. Amidst the scorching heat of a collapsing white dwarf, a cooling process unfolds, gradually dimming its once vibrant glow across the cosmos. This paradoxical dance between collapse and cooling is a testament to the intricate balance maintained by electron degeneracy pressure, which prevents further compression beyond the star's current size. A typical white dwarf cools below 3000 Kelvin after approximately 10 billion years, emitting thermal photons that subtly alter the cosmic microwave background radiation. These photons stretch across vast distances, their wavelengths elongated due to the expansion of space itself. The oldest known white dwarfs, some nearly 14 billion years old, have cooled enough to emit light in this manner, contributing to the faint glow that fills the universe. A white dwarf's cooling process is influenced by its initial mass and composition, leading to a range of thermal histories across the cosmos. For instance, a white dwarf with 10 times the mass of Jupiter cools more slowly than one with only half that mass, due to greater thermal inertia. This variation in cooling rates means some white dwarfs can take up to 15 billion years to cool below 3000 Kelvin, while others reach this temperature much faster, but at a lower final luminosity. The crystalline structure within white dwarfs, composed primarily of carbon and oxygen, contributes to their unique thermal properties. This arrangement resembles the molecular structure found in diamonds, making these stellar remnants some of the oldest and coldest objects in the universe. However, recent simulations suggest that as they cool, the internal pressure can cause unexpected shifts in the crystalline lattice, potentially leading to slight variations in their cooling rates. The faint glow emitted by cooling white dwarfs is part of this ancient light, subtly altering its spectrum with each photon. These thermal photons carry specific information about the star's age and composition, contributing precise measurements to the cosmic microwave background radiation. Each photon from a cooling white dwarf can shift the peak wavelength of the cosmic microwave background by fractions of a nanometer, an effect that has been detected in recent high-resolution observations. The cooling process within a white dwarf is not just a passive emission of heat. It involves complex interactions between particles at the quantum level. As electrons and nuclei settle into lower energy states, they release photons that travel through space for billions of years before contributing to the cosmic microwave background radiation. This radiation, first detected in 1965, provides a snapshot of the universe when it was only about 380,000 years old, long before white dwarfs began to form. The faint glow emitted by cooling white dwarfs is part of this ancient light, subtly altering its spectrum with each photon. These thermal photons carry information not just about the temperature and age of the star, but also about the conditions in the early universe. The cosmic microwave background radiation, once a uniform bath of energy, now bears the imprint of countless stars that have lived and died over billions of years. Each cooling white dwarf contributes to this subtle alteration, its thermal photons joining a chorus of signals from across the cosmos. This process is akin to adding layers to an ancient painting, where each brushstroke adds depth and detail. In the vast emptiness of space, these faint emissions are the only evidence that stars once burned brightly in distant galaxies, their light now stretched into longer wavelengths by the expansion of the universe. The cooling white dwarf drifts like a slowly extinguishing candle, its surface temperature dropping from over 13,000 Kelvin to below 3,000 Kelvin over billions of years. This ancient remnant of a once vibrant star now emits faint thermal radiation as it cools, each photon a testament to the long journey of stellar evolution. Amidst the cooling glow of distant white dwarfs, their vibrant heat a memory across the vast cosmic sea. The journey through these celestial realms now comes to a gentle close. Thank you for being here with us tonight, drifting among the stars. If you enjoyed this voyage, do consider subscribing and leaving a like. Good night, and may the quiet of space cradle your dreams.